In this lecture, we are going to learn something about uncompetitive inhibition. So we will see the kinetic mechanism behind this process. So here I have some figure where you can see you have enzyme. So just to follow the red ink. So you have some enzyme and then you have a substrate molecule. So they they associate together to form enzyme substrate complex. So just follow the red pen. And once you have this enzyme substrate complex, you have a space here which can accommodate your inhibitor. Inhibitor is shown here. So once the enzyme and substrate, they form the enzyme substrate complex. What we can think of like once your substrate bind to enzyme, let's assume that once you have this enzyme substrate complex, let you have to think that there is some conformational change which creates some new space, or if you want we can call it like a binding pocket that can accommodate your inhibitor molecule. So that's how this works. So this inhibitor will go and bind to this packet, this specific packet, and then to form enzyme inhibitor or enzyme substrate inhibitor complex. So in this case, this is your dead end complex or dead end molecule or molecular complex. So this won't react to give products. So that's the meaning of that. So what we have to focus here is the first process, enzyme plus substrate. So this one is completely reversible, and then the inhibitor which go and bind to the enzyme substrate complex to make enzyme substrate inhibitor complex. Again, this process is completely reversible. So these two processes are purely physical process. So they come together, they make a complex. So enzyme and substrate, they come together to form a enzyme substrate complex. So once the enzyme and substrate they comes together, you can expect some conformational change which creates some new binding packets which can accommodate or perfectly accommodate your inhibitor molecules. So your inhibitor will go and bind to that specific packet, binding packet, or or a molecular space to form enzyme substrate inhibitor complex. So that's how it works. And there are two physical processes. So enzyme and substrate, they associate to form enzyme substrate complex, and enzyme substrate associate with inhibitor to form enzyme substrate inhibitor complex. So and then like Michaelis-Menten kinetics, so you must have enzyme substrate complex in order to convert your enzymes into products. So just look at this part of the diagram. So you have your enzyme substrate complex here. So that will, so from here we get our product. So there is some chemical reaction happening here. So that's why this is only a forward reaction. It's not reversible. So it's completely irreversible reaction because we are going to expect some bond breakage, and that's why we will get completely a new molecule. So your substrate will be converted into product. Like exactly like Michaelis-Menten kinetics, the rate of the reaction is dictated by the enzyme substrate complex. So if you want, we can call this as K-catalytic. K-catalytic and enzyme substrate complex together with inhibitor that goes to enzyme substrate inhibitor complex. Let's say we have an equilibrium constant which is equal to Ki, and then here enzyme plus substrate that gives enzyme substrate complex, which is a completely reversible process, is associated with an equilibrium constant Km. So we have Km, Ki, K catalyst. So these two are equilibrium constant. This is the rate constant, and these two are associated with a purely physical process, reversible. K catalyst is the slowest, so is the rate constant that corresponds to the slowest reaction, and it is a chemical reaction, completely irreversible. So keep these things in the mind. So let's try to derive some expression that allows you to calculate the rate of the reaction for this type of reaction. So we have a uncompetitive inhibitor, so that will, okay, by the way, why we call it as uncompetitive inhibitor? If you come back to this diagram here, so you have an enzyme, you have substrate, and you have inhibitor. So this inhibitor will compete only with the enzyme substrate complex. It will never compete for the same binding packet of your substrate with the enzyme. So it will never compete with enzymes. It will compete only with the enzyme substrate complex. So that's why we call it as a uncompetitive inhibitors. So this type of inhibitors that competes only with enzyme substrate complex, we call them as uncompetitive. They will never fight for the space together with the substrate. Yeah. So that's the whole idea, and we can write this in a mathematical way. So as usual, we are going to give some notation. E for enzyme plus substrate, they associate to give enzyme substrate complex, and then your inhibitor will associate with or bind with enzyme substrate to give enzyme substrate inhibitor complex. So as I said, we have an equilibrium constant Ki, and here we have an equilibrium constant Km, and then this concentration of enzyme substrate complex that decides the rate of reaction. So enzyme substrate complex will give rise to enzyme plus product. So this is the place where your main chemical reaction or enzymatic reaction is happening. So you get a new molecule here. Let's put K catalyst. So that's the catalytic reaction. So these are like just a physical process, purely physical process. Okay. So again, similar to Michaelis-Menten kinetics, your rate of your reaction, or maybe we can call this initial velocity, like we used to call for all the enzymatic reaction. Initial velocity R0 will be equal to K catalyst multiplied by the concentration of your enzyme substrate complex. So R0, that's our initial velocity. So hope you are fine up till this point. So this is same for all the processes. So competitive or uncompetitive or non-competitive, for all of these reactions, the rate of the reaction or the initial velocity is dictated by the concentration of your enzyme substrate complex. And again, this complex is a dead end complex, enzyme substrate complex, what we can call dead end complex. So let's write the expressions for Km and Ki. So we know how to write for the equilibrium constant. So Km, you have to write concentration of everything on the reactant side, and then divided by the concentration of the product side, enzyme substrate. So likewise, we can write for the inhibition constant, Ki is equal to concentration of enzyme substrate, concentration of inhibitor divided by concentration of enzyme substrate inhibitor complex. So I think so far is fine, and we already know that. So for this type of system, at any instant of time, the total enzyme concentration inside the reactor will be equal to the freestanding enzymes plus the enzyme substrate complex plus enzyme which are associated with this inhibitor molecule, which is enzyme substrate inhibitor complex. Yeah. So at any instant of time, you can see either you can see your free enzyme, or you can see your enzyme is associated with your substrate, or your enzyme it can associate with your substrate plus inhibitor. So that will be your total enzyme concentration when we are going to deal with uncompetitive inhibition. So far good. So what we are going to do now, we are going to calculate the rate of the reaction. So let's try to do that. So we know what is ES. So let's rewrite. Enzyme substrate complex is equal to enzyme substrate divided by Km, and likewise enzyme substrate inhibitor complex. So we need to eliminate these parameters because we can't measure these values, enzyme substrate complex. So we cannot measure what's the, say at time t equal to time, what's the concentration of enzyme substrate inhibitor complex. We don't know. So that's why we will try to eliminate these parameters. And likewise the same, we cannot measure the concentration of enzyme substrate complex. So how many molecules of your enzyme are associated with substrate? This is something very difficult to measure experimentally. So that's why we have to eliminate them. So let's try to do that. So enzyme substrate complex will be equal to enzyme substrate concentration multiplied by inhibitor concentration divided by Ki. So let's substitute this ES. So let's call this as equation 1. So let's substitute the value of enzyme substrate and enzyme substrate inhibitor complex concentration in equation 1. So that should give E total, that should be equal to enzymes concentration plus how to do that, enzyme plus enzyme substrate complex. Maybe let's keep this enzyme substrate complex for the moment. Let's substitute for the K enzyme substrate inhibitor complex. So ES multiplied by I divided by Ki. So we can simplify this expression. So E total, that's equal to concentration of enzyme plus, we can, if you look at here, we have enzyme substrate complex as a common factor. So let's take it out. So you will get 1 plus I divided by Ki. So this looks okay so far. And we know that Km is equal to enzyme concentration multiplied by substrate concentration divided by ES. So therefore enzyme concentration will be equal to Km multiplied by ES divided by substrate concentration. So let's call this as equation 2. Let's call this as equation 3. So let's substitute equation 3 in 2. So what we are trying to do is we are trying to calculate the initial velocity K catalyst multiplied by ES. So we have to find some value for enzyme substrate complex. That's what we are trying to derive at the moment. So when we substitute 3 in 2, we will get E total. So take this value and substitute here. That should be equal to Km ES divided by S plus enzyme substrate complex 1 plus inhibitor concentration divided by Ki. So what we need to do is we need to find something ES is equal to what. So that's what we are trying to do at the moment. Let me try to do it in a paper, separate paper. Or we can just take the ES value as a common factor. If you look at this expression here, you have ES on the numerator, you have enzyme substrate complex here on the numerator. So we can take this common factor out. So that should be equal to E total should be equal to enzyme substrate complex. So we will have Km divided by S plus this whole value 1 plus inhibitor concentration divided by Ki. So what I'm going to do is I'm going to call this as alpha. So alpha is equal to 1 plus concentration of inhibitor divided by Ki. So let's give equation 4. So far good. So E total is nothing but enzyme substrate complex. So Km divided by S plus alpha. So therefore enzyme substrate complex concentration will be equal to E total divided by Km by S plus alpha. So we can expand this expression, so denominator side, so E total divided by Km plus alpha S divided by S. So all these are concentration of S. Okay, so again enzyme substrate complex will be equal to, so this one goes to your numerator, E total multiplied by your substrate concentration divided by Km plus alpha S. So now we have the value for enzyme substrate complex as a function of your inhibitor constant, which is related to alpha, and then we have our substrate concentration. This is something we can measure. Alpha we need to calculate, Km we need to calculate from the experimental data. So let's call this as equation 4, and we know R0, or the initial velocity, is equal to K catalyst enzyme substrate complex. So this expression comes from this part. So this is the where the main reaction is happening, where your substrate in the enzyme substrate complex is getting converted into new molecule products. So that's the slowest reaction. So that dictates the speed of your reaction. Yeah? So that's the rate controlling step, yeah, because you all know in chemistry the slowest reaction is the rate controlling step. So the initial velocity is K catalyst multiplied by enzyme substrate complex. If you don't know what's this, you have to listen to the mechanism and kinetics. I derived already in the classroom, and also it's also available on the YouTube. So let's call this as equation 5. So what you need to do is substitute this ES value here in equation 5. So substitute 4 in equation 5 and then solve for R0, or your initial velocity. So R0 will be equal to K catalyst multiplied by E total multiplied by your substrate concentration divided by Km plus alpha multiplied by S. So this is a very tricky expression. So let's try to make sense out of this. So this is nothing but your mu max, or your maximum initial velocity. So R0 is equal to K catalyst multiplied by E total multiplied by your substrate. So this will be equal to mu max divided by Km plus alpha multiplied by substrate concentration. So R0 is equal to mu max multiplied by your substrate concentration divided by Km plus alpha S. So this expression looks like a Michaelis-Menten kinetics. So I will write the expression just to so that you can easily compare. Mu max S divided by Km plus alpha S. Sorry, divided by S. So in uncompetitive inhibition, you have this alpha parameter is multiplied with your substrate concentration in the denominator. So that's the only difference whenever you are going to deal with a uncompetitive inhibitor. So what we can do with this expression? So how we were okay, if you are performing a enzymatic reaction without the presence of any inhibitor, if you plot substrate concentration versus your initial velocity, we all know you will get something like this. Yeah. So if you are repeating the same experiments in presence of an uncompetitive inhibitor, so where will be how your mu, or your initial velocity, will change with respect to your substrate concentration. So where this curve will be, it will be something like this or something like here. So we need to know so how to deal with this uncompetitive inhibitor. So one way to get some general idea is to maybe there is a way to do this. I will show you how to do it. So if you have initial velocity mu max substrate multiplied by substrate km plus alpha multiplied by s. So that's the rate expression that we derived, or the kinetic expression that we derived. So multiply by, sorry, divide by alpha on numerator, divide both numerator and denominator by alpha. So alpha is nothing but is a parameter which is related to your inhibition constant and to the concentration of your inhibitor. So R0 is equal to mu max divided by alpha multiplied by substrate concentration divided by Km by alpha plus alpha substrate concentration by alpha. So this is something equal to mu max by alpha multiplied by substrate concentration divided by Km by alpha plus substrate concentration. So this is for your uncompetitive inhibitor, and we know if you are performing a enzymatic reaction without any inhibitor, we know the rate expression is simply mu max multiplied by S divided by Km multiplied plus your substrate concentration. Yeah? So just follow the pink color pen. Just follow the pink color ink. So if you look at here, mu max by alpha, and if you compare here, you have mu max. So when you have a uncompetitive inhibitor, your mu max value will decrease by some amount, and that will be equal to your mu max divided by alpha. So that's what happens when you are going to deal with the uncompetitive inhibitor. Yeah? So your mu max will decrease by some amount, and that amount will be equal to mu max divided by alpha. So 1 by alpha, that's the factor. And then if you look at the Km value in a Michaelis-Menten expression, that is without any inhibitor, and when you are having an uncompetitive inhibitor, the Km value will be Km value is divided by some factor alpha. Yeah? So what it says is, like, when you are going to deal with the uncompetitive inhibitor, your Km value will also decrease by some factor. So and that Km value will be equal to Km divided by alpha. So that's the meaning of this type of expression. I think so how it will look like if we plot. So I will rewrite this expression here. R0 is equal to mu max by alpha multiplied by S divided by Km by alpha plus substrate concentration. So I'm going to draw the diagrams. So I will use the red pen for a reaction without any inhibitor. Your substrate concentration, your initial velocity. Okay, this is like inhibition free reaction, or no inhibitor. So you will have some mu max, and then exactly half of that will be here, mu max by 2, and that happens when your substrate concentration is equal to Km. So all the red color notations, or whatever I'm writing on in the red color pen, that corresponds to like pure enzymatic reaction. There are no inhibitors. And then let's assume we are repeating the experiment again in presence of an inhibitor. So this time we have an uncompetitive inhibitor. So your maximum velocity or your initial velocity, maximum initial velocity, that will change by a factor of alpha. So if you really plot those values, it will look something like here. Something like, okay, let me change the color. Look at the blue line. So this is your, that's your initial velocity as a function of substrate when we have an uncompetitive inhibitor. So this is uncompetitive inhibitor. And if you see here that mu max is dropped by some amount, so your mu max will be, so this part, so this part will be roughly equal to mu max. So this value will be equal to mu max by alpha, this one, and then exactly half of that mu max by alpha. So if you draw a line here, and then your Km value will also decrease. So that Km value will be equal to Km by alpha. So mu max by alpha, so that's this, and half of that somewhere around here, and you will achieve half of that initial velocity, which is mu max by alpha by 2, and that will happen when your substrate concentration is equal to Km by alpha. So we will reach, or our initial velocity will be equal to mu max by alpha by 2 when your substrate concentration will be equal to Km by alpha by, when your substrate concentration is equal to Km by alpha. So that's how we have to interpret for the uncompetitive inhibition. Yeah, so you have to remember these graphs. So this graph will give you some idea about uncompetitive inhibition. Uncompetitive inhibition. And then for uncompetitive inhibition, your mu m will change, your Km will change. So both will change. So if we have an uncompetitive inhibitor in the reactor, then your maximum initial velocity will change, and then your Km value is going to change. Yeah, and it changes by some factor which we know that's related to alpha, where alpha is nothing but 1 plus concentration of inhibitor divided by your Ki, which is an equilibrium constant or inhibition constant. So this is good so far. And then for competitive inhibitor, I hope you all remember. So you have your substrate concentration here, you have your initial velocity here. So this is like inhibitor or inhibition free kinetics. Inhibition free kinetics. And then when you have a competitive inhibitor, this is something you can expect. So this is a competitive inhibitor. Competitive inhibitor. So in this case, your mu max is same, or maximum initial velocity, it will not change, but your Km value will change. Your Km value will decrease. Km value will decrease, or how it will work? Km value will change, for sure it will change. I'm just checking. Km value will increase, Km value will increase because half of this value is here. So let's say your mu max by 2 is here. You just draw a line. So that's your Km value when there are no inhibitor. Just to follow the lines where I am drawing on the screen, and then this is the Km value. So your Km value will increase when you are dealing with the competitive inhibitor. Yeah? That's your Km value when you have a competitive inhibitor. This is a very tough topic, so you must have a lot of imagination plus some basic understandings on how the things comes together, how the molecules come together, how they make complex, and when the chemical reaction happens, and which complex decides the rate of the reaction. In this case, enzyme substrate complex. If you have more number of enzyme substrate complex, your initial velocity will be much higher. So that's how it works. So I hope you all remember all the points that I said until this point. So so far we studied about Michaelis-Menten kinetics, which is just a pure enzyme. We have an enzyme. We use that enzyme to convert your reactants into products, and enzymes are just a catalyst. So it won't participate in the reaction, but it will speed up your reaction. And then we already studied about competitive inhibitor. So in that case, your inhibitor will compete for the same site on the enzyme together with your substrate, and that's why we call it as a competitive inhibitor. And whenever you have a competitive inhibitor, it will not alter your maximum initial velocity. So it will alter your association constant or equilibrium constant, which is Km. Your Km value will increase if you are going to deal with a competitive inhibitor. And then again, we studied about uncompetitive inhibitor. So in this case, your inhibitor molecule will not compete with the enzyme packet with substrate, but it can associate with your enzyme substrate complex, and then it can form a dead end complex, enzyme substrate inhibitor complex, slightly bigger molecular complex. And when you have an uncompetitive inhibitor, your mu max is going to change, and then your Km value is also going to change. So your mu max will decrease, and then remember your Km value, your association constant, that will decrease, not increase. So when you have a competitive inhibitor, your Km value will increase. When you have an uncompetitive inhibitor, your Km value will decrease. So that's how it works. So far good. When we are going to solve the problem, you will know what will happen, what's happening to your Km value. Even if I made a wrong statement like Km value increase or decrease, you can check it mathematically. So I will give you some data like your initial velocity versus your substrate concentration for a pure enzymatic reaction, and then your initial velocity versus your substrate concentration in presence of a competitive inhibitor, and then another substrate. Sorry, no, it should be the other way around. I will give you substrate concentration versus initial velocity for a pure enzymatic reaction, no inhibitor, and then in presence of an competitive inhibitor, and then in presence of a non-competitive inhibitor. So I will give you some values like that. You have to plot substrate versus mu. You have to plot them, and then you have to tell me what type of inhibitor we are dealing with. I think so far good. So I'm going to stop now, and then in the next lecture I'm going to derive the kinetic expressions for non-competitive inhibition. This is even bit more complex, non-competitive inhibition. So there will be a lot of dead end complex in this type of, when we are going to deal with non-competitive inhibitors. So we will see that in the next class. So try to derive all these expressions in home. You may expect some derivations in the final exams. So instead of giving the formula, I will ask you to derive something, and then whatever you derive, you use that expression to solve a particular problem. So don't skip these derivations. Try to sit in home, watch the video 1 or 2 times, and then try to make the derivations by yourself. Okay, you have to derive the expressions for competitive inhibitor, non-competitive, and also the Michaelis-Menten kinetics, they are really, really important. Thanks for listening.